Yes, hello everybody to our statistics course. And last time we have started with our exercises, some revision on statistics, which you have learned in your first semesters, and we will go on with this. I think we had already until task 3, am I right? I think so. So this was this example with the harmonic mean, that if we want to calculate the price earnings ratio, that in this case, if we would just calculate here this price earnings ratio of our aggregated happens there. Of our, no, I cannot write anymore. Of our price earnings ratio of our portfolio of both investments in firm A and B. If we would calculate this by just our arithmetic mean, then we would not keep in mind that one firm with market capitalization of 200 billion euros is much larger than the other firm, which is much smaller, with only market capitalization of 800 million euros. And in this case, then we had to use the harmonic mean, and we saw that then in this case, of course, we have here the price earnings ratio of firm A is 25. It's much less than the price earnings ratio of firm B with 200. That then, if we use the right harmonic mean, of course, our averaged price earnings ratio is then much closer in the neighborhood of the price earnings ratio of firm A, and otherwise we would make a huge mistake, because then you see the price earnings ratio with the arithmetic mean moves much towards the price earnings ratio of firm B. Okay, but then we will go on with a more theoretic part, and task 4. Let me cut this, and then we start to show some nice properties of the arithmetic mean. So where is my instrument to cut this? I think here. Oh, sorry. Again. So for A, Oop. Let's start with A. This more or less means that our arithmetic mean is, so to speak, in the center of gravity of our sample distribution. So all differences of our data points xi calculated with respect the distance to the arithmetic mean will sum up to 0. So why is it called the center of gravity? Well, in this case, if you take a triangle and if you use all the lines coming from the middle into the corners, then all these lines also crossing in one point, and this is then the center of gravity in this triangle. And if you put your finger and above this point the triangle, then you can balance this triangle. Therefore it's called center of gravity. Property. Okay, and how can we show this property? Well, we just put in our definition, and for this we can write I from 1 to n sum over xi minus x bar. This is just a difference, so we can split these brackets into sum over I from 1 to n xi minus sum over I to n x bar. So, and this second part, this is just a sum from 1 to n, and the variable is a fixed number. So if we ask, for example, xi from 1 to 4, and the variable will be 2, what is this? This means that we should sum up 2 4 times from 1 to n. So this is nothing else than what? 2 plus 2 plus 2 plus 2 equals 8. So what will be then the sum over x bar from 1 to n? If you keep this in mind, and x bar is also a fixed number. Well, in this case, we just have to sum up n times the arithmetic mean. So this will be then minus x bar plus x bar plus x bar plus x bar over, and this n times. And what is sum over all values of our data points? can we write this also with the definition of the arithmetic mean? So remember what is the definition of the arithmetic mean? This is 1 over n, I from 1 to n over xi. And if you compare this with this expression, what you observe? Well, then of course we can multiply this with n, and then we have n times x bar is sum over I from 1 to n over xi. So this is obviously the same as this expression, so we obtain n times x bar. Here, in this case, we sum up n times x bar, so we obtain nx bar minus nx bar, and voila, this is of course 0. Quod erat demonstrandum. So, B. This is also a quite nice property of the arithmetic mean, because if we move all data points just with a linear transformation, that every single data point should be moved with the same parameters a and b. So to speak, we move this these data points 3 times the old data point plus 11 or something like this. And then of course we ask ourselves, what does this mean for the arithmetic mean? And what we want to show is that, again, also the arithmetic mean is moving in the same way as every single data point. And for this, we also just plug in the definition of our arithmetic mean. So, x bar prime equals, oh, this has to be, no I there. So this is a times, and now we plug in the definition, 1 over n, sum I from 1 to n, xi, plus b. For xi, we have to plug in the linear transformation. So a times 1 over n, I from 1 to n, equals, now there we are, x bar, xi, and then we, oops, sorry. Yep. This we want to show. We have to do it the other way around, sorry. So x bar this way. X bar prime is of course 1 over n times sum over xi bar, I from 1 to n, and now we plug in for xi bar our linear transformation. So we obtain 1 over n, I from 1 to n, a xi plus b. This is again in the same way we have here a difference. Here we have a sum, so we can split as a summation in the bracket. Thus we obtain 1 over n sum a xi I from 1 to n plus 1 over n sum I from 1 to n, and behind the summation b. Then of course this is a fixed number. We can move this outside. So we get a times 1 over n sum I from 1 to n I plus, and here again we have that b, just a fixed number, summation from 1 to n. Thus we have to sum up n times our b. So we obtain 1 over n, b plus b plus b, and this n times. Thus we obtain, this is again, have a look here, just the definition of our arithmetic mean. So we obtain a x bar plus 1 over n times b, and in the end a x bar plus, this cancels, b. And though we have shown part B of our task in 4, let's wait, it's just sitting, okay. And the last nice property, and this property is of course very important, because we see here, we also can ask, why do we use almost always the arithmetic mean? And one reason for this is this property in part C of our exercise, because we can show that if we use the arithmetic mean, then this means that we use this number which minimizes the sum of the squared distances of all our data points. And remember, we quite often use the squared distances for a measure of the dispersion of our sample, and especially you know that these squared distances are highly connected with the so-called normal distribution, and you know the importance of the normal distribution is due to the fact that although, or if you don't know what kind of distribution you have, if just your random sample, the number is high enough, then always the distribution of the mean moves approximately to the normal distribution. And therefore, this is a really nice property of the arithmetic mean. So then let's try to show this. How do we show this? Well, at first we just start and look if we just choose another number. So to speak, we suppose there would be another number m, and for this number m, we assume that the sum of the squared distances is smaller than the sum of the squared distances with the respect to the arithmetic mean. So we start and write down sum I from 1 to n xi minus m squared. And now, of course, we just want to calculate this with respect to the arithmetic mean, and in this case we put in, and this is quite often a nice trick in mathematics or statistics, that you add in a quite proper way just a 0. So we rewrite this to I from 1 to n sum over xi minus x bar plus x bar minus m squared. So we have nothing changed, nothing has changed, because this is just adding a 0. And if we do this, then we can use this as maybe a, and this is b. And what was a plus b squared? Do you remember? What is a plus b squared? This is, I don't know, 8th or 9th class in school. No idea? Yep. Oh, yeah, thank you very much. A squared plus 2ab plus b squared. And this we use just in this line, so we obtain sum over I from 1, and we have xi minus x bar squared plus 2 xi minus x bar times x bar minus m plus x bar minus m squared, closing brackets. And again, as in our a and b here, we have here just also a sum inside the summation operator. So again, we can split this. So this will be then sum from I to n xi minus x bar squared plus, and now This is just a constant, and this is just a constant. So the 2 is also a constant. And only here you have the summation parameter I. So all constants you can put outside the summation operator. So you obtain 2 times x bar times n summation I from 1 to n xi minus x bar plus, and here again we have the summation over a fixed number. X bar minus m are just fixed numbers. Squared is also a fixed number. So we just have to sum up x bar minus m squared n times, as we have done in the former cases. So now we see that this is also just a sum inside the summation operator. So we can split this. Let's take this out. Sum, oops. Sum over xi minus x bar I from 1 to n equals sum over x1 to n xi minus sum over x bar I from 1 to n. So what do we have here? Here we of course just have, remember our first two cases, this is just n times x bar. Because the definition of the arithmetic mean is 1 over n times sum over all xi's. This is again just a fixed number. If this is just a fixed number, then of course this is again n times x bar. So in this case we know that this is just 0. And if this is just 0, we see here that if we take some other number, that this number with that the square distances with respect to some other number than the arithmetic mean, the number m equals the sum over the square distances with respect to the arithmetic mean plus some positive number. X bar minus m squared is, of course, if m difference to x bar is just a positive number. So we have this is larger than 0. This is the square distance with respect to the arithmetic mean. So we can conclude that this xi minus m squared I from 1 to n is larger or equal to the square distances with respect to the arithmetic mean. And again, we have shown what we wanted to do. Did you have shown these properties already in your introductory courses? Because these properties are really important if we go on doing statistics. Anyhow, let's go to number 5. And in this exercise, we manipulate quite in the same way as before. All these summations. So what we want to do, is that we want to show why we quite often use in statistics not the summation divided by n of the squared distances for an estimator of the variance, but we use the division by 1 over n minus 1. So what we want to show is that if we take the expected value of this unbiased variance equals the true variance. So, or in words, the expected value of the estimated variance from our random sample equals the true variance. And this, of course, is a really nice property because we also want, to have an estimator where we can say, on average, with this estimator, we really get the right number which we are looking for. So this is what I'm written down here. And of course, we have to assume that we also don't know what is the true expected value of our random distribution. So then let's start. What do we have to do? Expected value of sigma hat squared equals, and now we just plug in our definition, expected value of 1 over n minus 1, sum I of 1 to n, xi minus x bar squared. Of course, we know that expected value is a linear operator. This is just a fixed number, so we can put outside this fixed number out of the expectation operator. 1 over n minus 1 times e of sum, and further on I will just leave out to write down the summation here from 1 to n. I will only write a summation sign. So xi minus x bar squared closing brackets. And now we also know that the expected value of our arithmetic mean, that this is also an unbiased estimator. We know that the expected value of our x bar is the true expected value of our sample. And for this, we can write that this equals 1 over n minus 1 expected value of summation xi minus x bar plus mu minus x bar. So this is more or less the same trick we apply here as in the former task, because this again is, because of this property, just 0. And then we can also say that, as before, this would be some, here squared, number a, and this would be a number b. And again, due to our formula here, we can write down 1 over n minus 1 expected value, open the brackets. What do we have? Oh, sorry. Not this. We have to put in here mu minus mu, that we have 0, of course. Up. That we have sum over xi minus mu squared plus sum over xi minus mu times mu minus x bar plus sum over mu minus x bar squared. And here we need also the 2. So then again we can split the summation 1 over n minus 1 expected value of sum x1 minus mu squared. Again we can move out the 2 and the mu minus x bar, because these are all fixed numbers. So we obtain plus 2 mu minus x bar sum over xi minus mu. This is just a fixed number, so we have to sum up these n times, means n times mu minus x bar squared. But in this case, we know also that we can split again. Let's take this sum here. sum over x1 minus mu equals sum over xi minus sum over mu. So this will be then nothing else as n times x bar minus mu. But this, you see, is just if you interchange this, the same as this part. So what do we obtain? 1 over n minus 1 expected value sum xi minus mu squared. This is the same as this, so but interchanged. So we obtain minus 2n x bar minus mu squared plus n, and since we have here a square, we can just also interchange these two numbers because it doesn't matter if we have a minus sign or not. So also x bar minus mu squared. But then we see that this and this it's the same, so we end up with 1 over n minus 1 expected value sum over xi minus mu squared minus n x bar minus mu squared. And now we can use this part here. Let's go to the next slide. Up. And that we can now split, since the expected value, the expectation operator is also a linear operator, we can split this into 1 over n minus 1. Let's have a look here. This first part, expected value of sum of xi minus mu squared, xi minus mu squared minus expected value of a fixed number. So, oops, n times expected value of x bar minus mu. So, of course, we have to keep in mind that the arithmetic mean in a random sample of random variables is also a random variable. So, x bar is also a random variable. This we have to keep in mind. So if we look at this part here, then of course we know that this is nothing else than the definition of our variance. So this is the true variance. This is sigma without a hat squared. So what do we mean? What do we know about the expected value of this part here? Well, from this, if every random variable is independent from each other, and this is always the assumption we make in statistics, that we have no correlation if we just ask people if they want to buy some good or something like this. Then of course we want that the answers of these people are not correlated. And in this case, we of course know that the expected value of x bar, oh here we need also a squared is the variance of the arithmetic mean. And this was this main result you hopefully have seen in your introductory courses, that this variance is scaling with the number of your random sample. That this is scaling down and equals 1 over n times the true variance of your random sample. So in this case, we obtain 1 over n minus 1 e sum, oh sorry, not sum xi, but sigma hat squared minus n times, and we obtain n times 1 over n sigma hat, sigma squared equals 1 n minus 1 n times sigma squared. This cancels out, minus sigma squared, so we can move out sigma squared, 1 over n minus 1 times 1 minus n minus 1 sigma squared. This cancels, and we obtain our result that the expected value of the estimated variance sigma hat squared equals the true variance. So I just interrupt the recording.